Hello and welcome back to a second part of lesson U2A3, Vector and Parametric Equations of a Plane. Remember in the first part we looked at how to physically draw a plane and learned the formula for the vector equation of a plane, which is R, that would be any vector on the plane, equals R0, that's the starting vector, plus a scalar multiple of the direction vector A plus scalar multiple of direction vector B. So in a more detailed form, then we had x, y, z representing the coordinates of the head of vector R, which is on the plane, equals x0, y0, z0, which are the coordinates of the head of vector R0, that's our starting vector, and this is our starting point, plus a scalar multiple of vector A with coordinates a1, a2, a3, and scalar multiple of B, which is b1, b2, b3. T and S are two scalar numbers. The parametric equations of the plane are described by the following equations. So x would equal x0, sa1, tb1 added together. Y would be y0, sa2, tb2 added together. And the coordinate z is z0, sa3, tb3 all added together. So now let's take a look at some examples where we have to create the equation, the vector equation of a plane. So in this question, we have to find vector and parametric equations of a plane if we knew that the plane will contain the points as indicated, 3 points, A, B, and C. Now remember that 3 points will make a plane, again, because we know that if you connect 3 points, then we form a triangle, and a triangle is a 2D shape, which means that it would lie flat on a flat surface, or would lie on a flat surface or on a plane. Now, in order to create the triangle, in order to find the equation of the plane, I would start off here with the general form of the equation. So I know what I need to input in here in order to define my plane there. So here we have x, y, z is any point on the plane, that won't change. We're going to need a starting point. This can be any of the given points. So it can be A or B or C. And then we have to define two direction vectors. Now remember direction vectors, if we have to create some triangle ABC that lies on a plane, can be considered, for example, these two. So I'm going to call them A, B, and C. So we can create different pairs of direction vectors. So we can choose AB and AC. We can choose BC and BA. We can choose CA and CB. It doesn't really matter. And we don't really need to actually have them start from the same point. So it can be AC and then it can be BA, the other vector. So I hope that this kind of gives a clear idea of how we're going to figure out our vectors now. So we need two of them. So for the starting point or starting vector, I'm going to choose point A. So -1, 3, and 8. And again, that's not the only point, which brings us to the idea that there is going to be more than one equation that can represent this same plane. Now for vector A1, I'm going to choose the direction vector AB. So I will say that direction vector A1 will be, direction vector A will be vector AB. Any multiple of vector AB can be the direction vector A, when you think about it. Because we're only interested in the direction, so it can be this one, direction vector can be this one, as long as they follow the same line, right? So AB, the coordinates can be found as -1 minus -1. So remember, from B we are subtracting A. And then for the y coordinate we have 1 minus 3. The z coordinate 0 minus 8. So A would be -1 minus -1, 0, 1 minus 3, -2, 0 minus 8, negative 8. For the next vector, I'm going to choose, say for example, vector BC. So for BC, which we're going to call our direction vector B, we'll have the coordinates. So again, remember, from C subtract B. So 4 minus negative 1 for x. For y, we have 1 minus 1. And then for z, we have 1 minus 0. So the coordinates of direction vector B would be 5, 0, and 1. So now that we have all the numbers, we can put them in. So we're going to say that x, y, z equals negative 1, 3, 8 plus t, 0, negative 2, negative 8 plus s, oh, just got this, have to be different numbers, and 5, 0, 1. Okay, so this is the vector equation. And now we are about to find the parametric equations. So parametric equations are built on vector equations. So we'll say that x equals negative 1 plus 0t plus 5s. Or simply said, x equals negative 1 plus 5s. Next, we have the equation for y, parameter y, which is 3, negative 2t, 0s. So therefore, we'll say that the equation for parameter y is 3 minus 2t. And last, we have the equation for parameter z, which is z equals 8. And then we have minus 8 and 1 for the direction vectors. So here we go. Eight minus 8t, and then plus 1s. So here we are, we have the direction vectors all in, and here are the parametric equations. Okay, so moving on to the next example, we have the next question. We have to identify whether these points lie on the plane. So for the points to lie on the plane, they must satisfy the vector equation. So I'm going to grab this vector equation here because we're going to need to use it. And I will plot it down here. Now you can use either parametric or vector equations if you want to prove whether or not a point lies on a plane. So for point P, which has the coordinates 14, 1, and 3, we're going to need to be equal to negative 1. This is very thin. Negative 1, 3, 8 plus t, 0, negative 2, negative 8 plus s, 5, 0, 1. So we can use the parametric equations to figure out the t and s values. If we obtain the same t and s values from each and every coordinate, then we would say that the point P fits into the equation. So we're going to say that 14 equals negative 1 plus 0t plus 5s. So 14 is negative 1 plus 5s, which will give the s value equal to, remember, 15 on one side. So letter S is a very difficult letter to use, especially next to a 5 here. So we have S equals 3. So I'm going to grab the parametric equations. They're easier to use. So we have the y coordinate, which is 1. equals 3 minus 2t. So that means 1 minus 3 equals negative 2t. Negative 2 equals negative 2t, and that gives the t value of 1. With an s value of 3 and t of 1, we're going to visit the parameter z and see if parameter z is happy with these two values of the scalars. So 8 minus 8 times 1 plus 3, that would be 3. And z equals the z value of 3. We're going to say that z coordinate is happy as well. So therefore, we're going to say that the point P lies on the plane. Now let's take a look at point Q. Okay, the coordinates of point Q are 14, 1, and 5. And what I would like you to take a look at here is the coordinates of P and Q and compare. So here is P with 14, 1, 3. Here we have 14, 1, 5. Remember that using the x and the y coordinates here, we figured out the values of s and t to be 3 and 1. So they give a value of z equals 3, which equals the same z coordinate as P. And that's what made it possible for us to say that P lies on the plane. Just by looking at the z coordinate here, which is 5, then we can tell that point Q most likely is not on the plane. But let's take a look at each equation and see how that works. So we're going to say that 14, we're using the parameter equation for x, negative 1 plus 5s. So 15 equals 5s, s equals 3. So next we have y equals 3 minus 2t. So again, we have y value of 1 equals 3 minus 2t. So that will give negative 2 equals negative 2t, which makes the t value 1. So with these two values, we're going to go build the equation for z. Remember, this is z. We have 5, which must equal 8 minus 8t plus s. The value of t is 1, the value of s is 3. As you can see here, we get 0 plus 3 or 3, and you can tell that the sides are not the same, which means that the z coordinate, it cannot be accommodated or cannot fit with this s and t values that work for x and y, which tells us that P is not on the Q. Point Q is not on the plane. So in the next equation, we have to solve a problem involving a plane. We are given the vector equation of a plane. We have to find the point of intersection between the plane and the z-axis. So let's rewrite the equation first. We have 6, negative 2, and negative 3, plus s, 1, 3, 0, and then plus t, 2, 2, negative 1. So we have to find the point of intersection of this plane with z-axis. So we're going to need the coordinates of a point on the z-axis. And we're going to let that point be some point P. Now, on the z-axis, the x-coordinate is 0, the y-coordinate is 0, the z will be an unknown number. So at the point of intersection, which means that the point of intersection will be on both equations, right? We will see a common point, which means that this must fit into the equation of the vector equation of the plane. So the point of intersection must fit the equation of the plane. So here we go. We have 0, 0, z equals 6, negative 2, negative 3, plus s, 1, 3, 0, plus t, 2, 2, negative 1. So let's build the parametric equations. so that we can figure out the values of s and t. So we have 0 equals 6 plus s plus 2t. So s plus 2t equals 6. Next, we have the parameter y. So we have 0 again equals negative 2 plus 3s plus 2t. So we have 3s plus 2t equals 0. And last, we have the coordinate z, which means z equals negative 3 plus 0s minus t. So z will be negative 3 minus t. So let's check and see what we can find. In this case, remember the goal is to find z. And to find z, we're going to need the value of the scalar t. So see that here we have two equations that connect s and t. So we are going to put the two equations together to solve for s and t. So I'm going to bring the two equations next to each other, and I will try to use elimination. And the reason why I made that decision so quickly is because I see that I have two terms with same coefficient. So if I subtracted the second equation, I can eliminate the variable t. So we have s minus 3s negative 2s equals 6 minus 0, which is 6. Remember, here we have nothing. And that would lead us to s equals negative 3. Now, if s equals negative 3, then we can use either equation. I'm going to use equation 1, s plus 2t equals 6. Substitute. 2t equals 6 over minus negative 3 is a 9, so t is 9 over 2, or 4.5 is just fine. So we're going to say that coordinate z is negative 3 minus 9 over 2, or negative 6 minus 9, negative 17 over 2. So the point of intersection would be at 0, 0, and negative 17 over 2. All right, so the last example is about representing the equations of a plane from a point and a line. So in this case, we are given the coordinates of a point, and we have to find vector and parametric equations of a plane that contains this point and this line. Now we're going to say that the vector equation again will be x, y, z, any point on a plane, would equal a positive 1, negative 5, 1. So the coordinates of point P. And then plus the direction vectors A and B. So what we have in here is some line L. And what we know about this line is a point and a direction vector. Since the line is on the plane, then the direction vector of the line can serve as a direction vector of the plane. So this one here, I choose to call the direction vector A. So negative 1, 1, and 0. Now we are going to need another direction vector because we are finding the equation of a plane. So that's unknown. Now remember that point 1, 1, 1 will be a point on the line which is located on the plane. So this will be a point on the plane. The point P is a point on the plane because that's given. So by connecting the starting vector of the line with the given point, we can create a second direction vector. So for direction vector P, we are going to use the coordinates of P, and I'm going to call this point A. So we're going to say that vector AP can serve as the direction vector B. So let me write it nicely. Which would equal So from A, 1 minus 1. And then we have 1 minus negative 5. And last, we have 1 minus 9. So that would be 0, 6, negative 8. So we're going to say this can be used as a direction vector B. Remember, any multiple of this vector can be used as a direction vector. And just for the fun of it, I am going to say that, even 0, 3, negative 4 can be another possible direction vector. We're going to leave it at the first one, okay? So we won't confuse or mix things up. But here we go. We have x, y, and z equals 1, negative 5, 9, plus t, negative 1, 1, 0, plus s, 0, 6, and negative 8. Now the parametric equations, again, we know that we are connecting the similar coordinates together. So 1 minus t plus 0s, right? So that's a 0. For the parameter y, we have negative 5, 1, and then 6 in here. So negative 5 minus t plus 6s. And the last parameter, z, 9, 0, and negative 8. So we'll say that z equals 9 plus 0t minus 8s. So here go the 3 parametric equations of the plane, of our plane. So I hope you find this useful and I hope this made sense. Thank you for watching. Bye for now.